Okay, hello everybody. We'll get started now. Can someone confirm that they can hear me, please?
Yes, we can hear you.
Okay, thank you. So I'll start out with just a repeat of the announcement I made last time about a particular problem, or maybe it was a couple problems on homework 4. The top drawing of the vector that you add to the problem will not be accepted probably by mastering physics, but the bottom one will. So the vector needs to come off of that vertical plane. Okay, so today we're going to switch gears and start talking about relativity. And two of the questions that we're going to pose and answer today are what happens if you measure an electromagnetic field, or wave, I should say, as you're running alongside it very quickly. And the second thing we're going to answer is what happens if I measure two events that happen simultaneously and you measure those same two events and you say that they don't or did not occur simultaneously. Can we both be right? So special relativity, the special in special relativity means it's a special case. And the case is what happens when reference frames, which I'll describe in a minute, move at a constant velocity with respect to one another or relative to one another. And these are known as inertial reference frames. So mainly what that means is that these reference frames or coordinate systems do not accelerate with respect to one another. If that happens, then instead of special relativity, you have general relativity. And that's beyond the scope of this course, so we won't be talking about that. Special relativity, unlike general relativity, is not mathematically complex, but conceptually it can be pretty challenging because as you'll see, it forces us to rethink really deeply held notions of space and time. So as a way to introduce this, I'm going to start out talking about a different kind of relativity called Galilean relativity. This is the one we're all used to and applies when things are moving slowly and we don't have electromagnetic radiation involved. So first I need to define what a reference frame is. And it's basically a coordinate system. So it's just a set of X, Y, and Z coordinate axes that go off to infinity. And in that coordinate system, we can measure the position and time as accurately as we need to. And the person who's doing the measuring is at rest in his, her, or its reference frame. So for example, let's say I walk at 1 meter per second towards you, and you're standing still. So in your reference frame, you would measure my velocity to be 1 meter per second. Sort of obvious. What happens though if I walk 1 meter per second towards you and you walk 1 meter per second towards me? So we're walking towards each other. So then in your reference frame, you're looking at me and you measure my velocity to be 2 meters per second, right? Because you're walking towards me and I'm walking towards you, each at 1 meter per second. So if you do like some range finding or something to see how fast I'm moving relative to you, my velocity will be measured to be 2 meters per second. So I'd like you to answer this poll then. What is my true velocity? Okay, get your votes in. All right, so most people chose B, which is 1 meter per second. That is incorrect. And the reason that's incorrect is because the velocity requires that you measure delta x and delta t and take their ratio. And that in turn requires some coordinate system to be defined so that you can measure that delta x and delta t. And that coordinate system could be moving with any velocity, and it would still be a valid coordinate system to be using. So you could be walking towards me, or you could be walking away from me when you make the measurement. There is no true velocity. There is no true reference frame. So just to get into a little more detail with reference frames, because we're going to be using them extensively, there's some pictures on the right-hand side of the slide showing two reference frames, which are typically labeled as S and S prime respectively. And the S reference frame is usually the one that's taken to be at rest. That's the one where you might, as the measurer, be standing. And then reference frame S prime is the one that's moving with some velocity, usually labeled lowercase v, with respect to the reference frame S. And it is, by convention, assumed that S and S prime, these two reference frames, their origins line up and they coincide right when t equals 0. And we also take v to be a constant because these are inertial reference frames. So there's no acceleration going on. S prime moves with a constant velocity of some value with respect to S. And just to keep things simple, we don't consider the case where S prime could be moving in some random direction. We just assume it's moving sort of parallel to the x-axis. So the x, and in this case, the x prime axes line up. They line up, everything lines up perfectly at t equals 0. And then as time evolves, the S prime reference frame moves in this picture to the right with the x and x prime axes right on top of one another. So just as an aside, can anyone tell me what prevents a true inertial reference frame from actually existing on Earth? You can put it in the chat. What is it about Earth, that being on Earth, that prevents a true inertial reference frame from actually existing? That's right. So Earth is spinning. And because it's spinning, that means that we are all being constantly accelerated. So that's one reason why there is no true inertial reference frame on Earth. Okay, so the next thing that I want to talk about are transformations that you can do from one reference frame to another. So if something happens in one inertial reference frame, and that's something, it could be a flashlight being turned on and off, right? That is called an event. So an event that happens in a reference frame S at some position x and at some time t, where and when does it happen in some other inertial reference frame S prime that could be moving with some velocity with respect to S? And we're going to assume that S prime has a velocity v in the plus x direction, just as we drew in the previous slide. So in other words, how are the quantities x and t, which give you the position and time in reference frame S, related to x prime and t prime, which give you the position and time measured in the moving frame S prime? So this picture down here illustrates what we're talking about. So the event here is a firecracker exploding at some time, t. And what would be measured by these two reference frames? So at time t equals 0, S and S prime coincide. And then at some time t, the firecracker explodes. So during that time t, the reference frame S prime has moved a distance v times t. So distance just equals velocity times time. In that case, the distance moved is the distance moved by the S prime reference frame relative to the S reference frame. And you can see then that X, the position at which this firecracker explodes, is going to be different from X prime, the position at which the firecracker explodes in the S prime reference frame. So X tells you where it explodes in the S reference frame, X prime where it explodes in the S prime reference frame. And just as an aside, the perpendicular distances Y prime and Z prime are all equal to their unprimed counterparts Y and Z. So Y, in this case, we just drew the 2 dimensions, X and Y, and X prime and Y prime, and Y prime is equal to Y. So it's just moving parallel to the X axis. So we can write down these expressions, and you can make a transformation from X prime to X, or from X to X prime, either way. And it's the expressions are hopefully pretty obvious once you realize what the setup is for these 2 reference frames. So X is just equal to X prime plus V times T. And you can see that from here. This long arrow here is X, and these 2 arrows added together will equal X. Vt plus X prime will equal X, and that's exactly what is shown in this expression here. And in this expression here, just sort of inverted. Okay. So those transformations are for position. What would the transformations for velocity be? And the conventions that we're going to follow here are that the symbol V is used for the velocity of one reference frame with respect to the other. So, in our case, we're standing in the reference frame S, and S prime moves past us with velocity V. And we're going to use the variables U and U prime for the velocities of objects in the S and S prime reference frames, respectively. So if we start out with these expressions up here for the position transformations, all we need to do is take the derivative. And if we do that, we will get the velocities, which we call U sub x and U sub x prime, in those reference frames. And you can see, not surprisingly, that the transformations, the velocity transformations, look like that. So U of x is U of x prime plus V. So this is basically what you were doing when you calculated how fast I was walking in the previous example we discussed. If I'm moving 1 meter per second towards you and you're walking 1 meter per second towards me, the velocities that get added up provide you with, give you 2 meters per second of velocity that you would measure in your reference frame. Okay, so this is sort of the intuitive way that we deal with things moving around us. So let's imagine that we have an object in frame S and it undergoes an acceleration, A. What would we see in frame S prime? So I'll let you do that poll. So remember how you get from velocity to acceleration. Take a derivative with respect to time. And remember also what things in, say, this expression depend on time and what things are constant. Okay, get your votes in. All right, so we have a roughly equal number of people saying B and C. The correct answer is B. If you take the derivatives with respect to time on both sides of, say, this expression here, what you'll get on one side is the acceleration a. And then if we take the derivative of the right-hand side of this equation up on top here, then we'll get something that looks like acceleration. That's a prime. And then we have dv dt. But remember that v is a constant. And so this derivative is just 0. And consequently, we have that a is equal to a prime. Or a prime is equal to a. Same thing. This is an important conclusion. And the reason this is an important conclusion is because if a and a prime are equal between any two inertial reference frames, then we also can conclude that f equals ma is equal to f prime is equal to ma prime. So we're basically using a and a prime equal. We're assuming that the mass doesn't change because we're moving. We wouldn't expect the mass to change. So we then have that the same expression that gives us all the laws of mechanics, that's F equals ma, like conservation of energy, conservation of momentum, that all flows from F equals ma. And since F equals ma equals ma prime equals F prime, we can say, therefore, that the laws of mechanics are all the same in all inertial reference frames. So that's the Galilean principle of relativity. The key phrase here, well, the whole phrase is important, the whole sentence is important, but the key phrase is that we're focused on the laws of mechanics here. And Einstein extended that to cover not just mechanics, but also electromagnetism, as we'll see in a few minutes. Okay, so let's test our understanding of the Galilean principle of relativity. So imagine you have two balls moving toward one another along the x-axis. So there are two balls coming in like this towards each other. And the initial total momentum of the isolated two-ball system is some value in s. Sorry, 10 kilogram meters per second. And the two balls collide head on. So the way this could be the case is if one of them was moving a lot faster than the other. So then we have some net momentum pointing over that way. If this ball is moving faster than the other, they're moving towards each other, but one of them is moving faster towards the other, or one is more massive than the other. You can have a net momentum, obviously, in a head-on collision. So what must be true about this process in the reference frame S, as I just described, okay, where we initially measure, say, 10 kilogram meters per second, and S prime? So the laws of mechanics need to stay the same. It might be helpful to think about some kind of a limiting case where instead of a net momentum equal to, say, 10, you could have the net momentum equal to 0. Okay, so the two particles come in and they have equal and opposite momenta, and maybe they hit each other and bounce off if it's an elastic collision. What would happen if you were then running past this situation as these two objects bounced into one another and then went apart? What would you measure for their total momentum? Okay, so most people said sort of intuitively that that A is the correct answer. And that's kind of what you might think, but think of the example I just told you. If you run past two balls that are bouncing apart from one another. So if I'm standing still with respect to them, I see this happen. I say, oh, the total momentum is 0 before and after. But what if you're running by and you're measuring that? So if you're running in that direction, you will see these two balls moving in the opposite direction. And in fact, they will both be moving in the opposite direction. They'll be looking like this to you. And what will the total momentum be that you measure for those two balls? Will you measure that total momentum of those two balls to be 0 like you did in this reference frame, in the S reference frame? And now you have to imagine there's an S prime reference frame that could be you running by, looking at these two balls bouncing off of each other. What do you measure for their momentum? So the answer is that what you measure is that the momentum is conserved. You measure that the momentum before and after the collision is the same, but you don't necessarily measure the same value of momentum before and after in the two reference frames. In one reference frame, you might measure 10 before and 10 after, because momentum is conserved. And if you are running past it at, I don't know, 10 meters per second, you might measure that the total momentum at the beginning is 20. And then that the momentum after the collision would also be 20. So in the first reference frame where you measure 10 before and after, momentum is conserved. In the second reference frame, which is running past this experiment for some reason, you measure that the initial momentum is 20, and you will therefore measure that the final momentum is also 20, because what has to stay the same between reference frames, inertial reference frames, is that the laws of mechanics continue to be obeyed. Okay, so conservation of momentum, conservation of energy, those are things that need to stay the same, regardless of your reference frame. Okay. So let's now explore what happens if we include light in this discussion, or more generally, electromagnetic radiation. So this is what's called Einstein's principle of relativity. Before we actually write something down that is that principle, I'm going to give you some background, how people thought about this historically. So over 100 years ago, people knew that light was a wave. It interfered, it diffracted, and so on. And other waves that they were familiar with, mechanical waves, like sound and water waves, were known to travel in a medium. And in fact, it was observed that sound, for example, traveled considerably more slowly in air than it did, say, in steel. So the stiffer the medium, the faster the wave traveled. It was presumed that light also traveled in a medium, and the name of this medium was dubbed the ether. And the ether had some pretty peculiar properties. So for example, because light waves were known to travel really, really fast, for one, the medium had to be really, really stiff. And because we could see stars, and we knew that light traveled through space, not only did this medium have to be really, really stiff, much, much stiffer than steel, but it also had to be everywhere. So these two things, I mean, in retrospect, just made no sense that people were able to hold these two ideas in their heads at the same time and say, yeah, these are not mutually exclusive. We can find a solution that will satisfy these two criteria, that it's everywhere and that it's exceedingly stiff. All right. At the same time, Maxwell's theory of electromagnetism, which had been around already by the time this discussion was starting for about 50 years, told us that light in vacuum traveled only at one speed. So if you solve the equations for electromagnetism, electromagnetic waves travel at the speed c. And it's given by this expression. And it's about 3 times 10 to the 8 meters per second, roughly. So therefore, if you make the assumption, by the way, the wrong assumption, if you make the wrong assumption that light had to be traveling in some medium, and that medium was ether, then if light is moving at the speed c, only if you're in the rest frame of the ether, so if you're moving along with the ether somehow, then you will measure c for the speed of light. Otherwise, you'll measure v or c plus or minus v, depending on which direction you're moving with respect to this ubiquitous ether. And Maxwell's laws would only be valid in the ether's reference frame. So what people were trying to do is measure this effect. And the way they did that is by using about a ton of liquid mercury in a bath on which they floated an interferometer. And we talked about how interferometers work. What they did was they used the interferometer to try to see if the speed of light along one arm of the interferometer was different from the speed of light along another arm of the interferometer as the Earth moved around the sun. At varying times, it would in principle be moving towards the ether, and at other times away from the ether, if the ether existed. So this is one of the most famous negative experiments ever performed because they obtained a negative result, meaning they did not see any change of the speed of light over a period of a year of measuring this thing with a ton of mercury. And ultimately, this is one of the main reasons why the idea of the ether fell away and fell out of favor. The other thing you could do, and this is something apparently Einstein did when he was about your age. So he did this thought experiment. He said, okay, electromagnetic waves are made of changing electric and magnetic fields. And you can imagine, you know, the electric wave sort of going like this, up and down towards you. At the same time, the magnetic field is moving in some perpendicular direction. And the whole wave is moving in the direction that's the cross product of the electric and magnetic field directions. So what would happen if you could travel alongside an electromagnetic wave at a speed of c? So if you're looking at the electric field going up and down, that's part of the electromagnetic wave, and you situate yourself, and it's moving at speed c, and you're running alongside it at speed c, then let's say you just happen to line yourself up with one of the peaks of the electromagnetic wave, you will just be moving along with that peak. So here's the peak, and you're just moving along with the peak. And what you would then see, if you're looking at this electromagnetic wave, is something that isn't changing, right? You just see the peak because you're looking out, you know, you're moving at speed c, electromagnetic wave is moving right alongside you, and you know, you're lined up with the peak, and that's what you see. And it doesn't change. So this is a logical inconsistency because the only way that an electromagnetic wave sustains itself is by having the changing electric field induce a change of magnetic field and vice versa. And you presumably saw this in physics 212. But if you're moving alongside at velocity equals c, the electric and magnetic fields will both be constant, and therefore there can't be an electromagnetic field. Okay, so that's where Einstein came in with the principle of relativity, like version 2.0. So we're going from the Galilean version to the Einsteinian version. And his assertion was that all the laws of physics are the same in all inertial reference frames. So emphasis on all. So this explicitly includes Maxwell's laws, which stipulate that light only moves at speed c in vacuum. So if we accept this principle of relativity, then we must have the velocity of light equal to c in all inertial reference frames. And this will seem bizarre, and I'll show you that in a minute. But first, let me explain why I am referring to Albert Einstein as Al. So I was visiting my parents in New Jersey. They live in Edison, or lived in Edison, which is right near a town called Metuchen. And Metuchen had this restaurant that my wife and I went to, and we walked into the restaurant. And my wife really likes to sit next to windows, so we asked for the seat next to the window, and we're sitting there. And the owner came over and started talking to us, and he asked me what I did. And I said I was a physicist, and his eyes like really lit up. And he told me that the place where I was sitting was where Einstein used to sit whenever he went from Princeton to New York City on the train. He would get off at around lunchtime in Metuchen and come to this little restaurant and eat right there in that window seat. So, you know, Einstein and me were like this. So that's why I get to call him Al. All right, so I'm not being cheeky. We really are best friends. Anyway, so if we want all the laws of physics to be the same in all inertial reference frames, then the speed of light has to be constant, has to be invariant. That's another way of saying has to be constant in all inertial reference frames. So what does this mean? So let me just give you one example. So imagine you have a spaceship moving towards you at half the speed of light, so 0.5 c. And it's moving towards you and it flashes its headlights at you because, you know, spaceships need headlights, okay, before it passes by. So you will measure the speed of the light pulse coming at you to be v equals c, not 1.5 c, even though the thing, the spaceship that emitted that light, was moving at half the speed of light. Okay, I'll let that sink in a little bit because it's weird. Now, we have never actually gotten spaceships that move that fast and made that measurement. However, we can make related measurements of particles moving very fast. And in particular, there's one measurement that can be done pretty easily. If you have a particle called a neutral pion, which are fairly common in particle physics, and they are created in cosmic ray air showers whenever protons, you know, bash into our atmosphere, which happens very, very frequently. Lots of particles called pions are created. And it's known that a neutral pion, abbreviated with this pi 0 symbol, decays into two back-to-back photons. And when it decays at rest, so if you're just standing there and there's a neutral pion in front of you, those two photons will go up away from the pion, each moving with a velocity equal to c, assuming this all happens in vacuum. If this pion is going past you at a really high speed at 0.999 c, and then it decays into two photons, and you measure those two photons and their speed, you will also measure that they are moving at the speed of light c. You might think, oh, the one that's going in the forward direction, you know, in the same direction as the pion, would be moving at 1.999 c, and the other one going in the backward direction would be moving at 0.001 c, but you'd be wrong. Those two photons will move at c. So there have been lots and lots of measurements that provide irrefutable evidence that light moves with a velocity v equals c in vacuum, no matter what the reference frame. It doesn't matter if that pion is sitting still or if it's moving past you at 0.999 c. Someone put in the chat, if the ship was traveling at 99.99999% the speed of light and turned on its headlights, would we still measure the light pulse to be c? And the answer is yes. You can put as many 9s there as you like, and the answer will still be yes. Okay, let's explore the implications of this. And we're going to start out by thinking low velocities and sort of Galilean, with a bicyclist passing a tree and a lamppost. And then we're going to use that discussion to think about what happens to light. So the first column here is the reference frame S. And what I'm doing is I set my timer equal to 0 right when the bicyclist passes the tree. And then sometime later, after delta t, the bicyclist passes the lamppost. And that happens, at some value of x. So the distance between where the bicyclist was in my reference frame, I'm just standing on the ground here, where the bicyclist was when she passed by the tree and where the bicyclist was when she passed by the lamppost, gives you delta x. So the bicyclist velocity obviously is delta x divided by delta t. And remember, we use the symbol u because that's the velocity of something moving in this reference frame. And this is the S reference frame. Okay, now what happens in this other reference frame where you could imagine that we're driving by in a car, moving at some velocity. So in that case, we have, say a ruler or a tape measure attached to the side of the car, okay? And we look out at the side of the car and say, okay, the bicyclist is right at the tree. So I'll start my watch and I'm my stopwatch. So that stopwatch is going to measure delta t prime, the time that elapses in the S prime reference frame. And I look down at the tape measure that's attached to the side of my car. And I say, okay, that's the x position, x prime equals 0 for the bicyclist. And then sometime later, the bicyclist crosses or goes past the lamppost. And I make a measurement of where the bicyclist is and when the bicyclist passed the lamppost using x prime and t prime. So I use the tape measure that's attached to the side of the car that could be driving along, and I use the watch that I have. And what will I measure? So in particular, what is the relationship between delta x and delta x prime? What is the distance that I measure in the S reference frame versus the S prime reference frame? So one way to help think about this is in the limiting case that the S prime reference frame, which is you sitting in your car, are moving along at exactly the same velocity as the bicyclist. So in that case, when you look out of the mirror, when you look out the window and you say, okay, x prime equals 0, bicyclist is at the tree. And then sometime later, the bicyclist passes the lamppost. And of course, you're going the same speed as the bicyclist. So you're going to see the bicyclist, you're going to see the lamppost the same time the bicyclist does. And then you look down at your coordinate axes and you say, oh, I'm still at x prime equals 0 here. The bicyclist is still at x prime equals 0 when the bicyclist goes by the lamppost. So in that case, delta x prime would be equal to 0. So in general, delta x and delta x prime are not the same. And in the case that we've shown here, where the velocity of the car or the S prime frame is slightly less to or equal to the velocity of the bicyclist herself, we will get that delta x is larger than delta x prime. So what does that mean for the velocities u and u prime? So if you look back here, if delta t and delta t prime are equal to one another, which you would sort of naively expect them to be. So that's, if you have a stopwatch and you're standing on the ground, you say, okay, time t equals 0, the bicyclist passed the tree, and then you hit the stopwatch again, and that gives you delta t for when the bicyclist went by the lamppost. And then you do the same thing to measure delta t prime, but you have your stopwatch in the car with you, and you're looking out the window as the bicyclist goes by the tree and then the lamppost. So in one case, you measure delta t, and then the other case, delta t prime. And the natural assumption is that delta t and delta t prime are equal. So if that's the case, and delta x and delta x prime are not equal, then you would not expect u and u prime to be the same, right? Because u is delta x over delta t, and u prime is delta x prime divided by delta t prime. So if delta t and delta t prime are the same, but delta x is larger than delta x prime, we expect u to be larger than u prime. And that's borne out by experience, right? If you look in the reference frame S, you're going to see the bicyclist moving by with some velocity u. You're just standing there watching the bicyclist go by. But if you drive right alongside with the bicyclist and you look out, the bicyclist looks like she's not moving. I mean, you can see that the ground is moving because you're driving along, but if you just focus on the bicyclist and nothing else, if you're driving at the same speed as that bicyclist, then you're going to say the bicyclist is not moving with respect to me. So the velocity there, u prime, will be 0 in that particular extreme case. All right, so let's now make a bit of a leap. And instead of a bicyclist, imagine that this bicyclist is a light wave. Okay. And we're doing the same thing now. We measure on the ground, we stand there, we watch the light wave go by, and we measure when it passes the tree and then when it passes the lamppost. And then we do the same exact measurement, but we're moving in some reference frame S prime and watching the light wave go by the tree and the lamppost. How are things different when we have light involved instead of a bicyclist? So one thing that's the same is that delta x is going to be greater than delta x prime. The thing that's going to be different is that because we now have a light wave, independent of which reference frame we're looking at the light wave and measuring its speed, we will measure c. So we will always measure that the speed of light is equal to c, regardless of how fast we are moving relative to that light. So, given that we have the velocity in the S reference frame is delta x over delta t, and in the S prime reference frame, it's delta x prime over delta t prime, and we now know that for light, because of Einstein's principle of relativity, but mainly because of Maxwell, who wrote down the electromagnetic equations, which told us that the speed of light is always c in vacuum. Given those facts, we know that this u and this u prime are the same. They're both c. We also know that this delta x and this delta x prime are not the same. So if u and u prime are both c, okay, but delta x and delta x prime are not the same, what does that tell us about delta t and delta t prime? What do we have to conclude from that? So let me ask you that as a quick concept question. Okay, get your answers in, please. Okay, so most people chose the correct answer here, which is C. So delta t, must be greater than delta t prime. Now, this is a bit of a strange result, actually, because it means that the time interval we measure is not the same if we are moving with respect to some set of events. So here the two events are bicyclist passes the tree, then next event, bicyclist passes the lamppost. The time between those two events is not necessarily the same if we are in a moving reference frame when we measure it. That's kind of weird. So the next couple of slides have some definitions which basically define what an event is, and it basically says that we can synchronize clocks doing sort of a thought experiment throughout space. There's a way to do that. And once we have done synchronization of the clocks, then we can make measurements that we need to make in order to demonstrate the impacts of special relativity. So I'll let you read those two slides on your own. They're not very complicated. The reason that we're going to now talk about something called simultaneity instead of time is based on something that Einstein said. He basically made the observation that simultaneity and time are really talking about the same thing. But simultaneity is a more rigorous way of thinking on it. Basically, I'll just read this quote. So he said, "We have to take into account that all our judgments in which times play a part are always judgments of simultaneous events. If, for instance, I say, that train arrives here at 7 o'clock, I mean something like this. The pointing of the small hand of my watch to 7 and the arrival of the train are simultaneous events." Okay, so in what follows, we're going to talk about simultaneity. And let me go through one example here where we have synchronized clocks, and we're going to use them to determine whether two events were simultaneous in a given reference frame or not. So the situation is as follows. There's a tree and a pole, and they're 3 kilometers apart, and we know how fast light moves. And each one of these objects, the tree and the pole, are hit by a separate bolt of lightning. You're standing exactly in between the tree and the pole, so 1.5 kilometers from the tree and 1.5 kilometers from the pole. And you see that these two lightning bolts arrive to you at the same time. So you rightly conclude that they simultaneously struck the tree and the pole. So now what will your friend, who is unwisely standing under the tree during this lightning storm, say about the events? Will your friend say that they're simultaneous or not? So let me do a quick poll on this. And you can assume that you both have really accurate measurement devices. So light traveling from 3 kilometers away at 300,000, 3 times 10 to the 8 meters per second, will arrive in microseconds, and you'll be able to measure, when it arrives, to infinite accuracy. Okay, so most people answered B, which is no. And I expected this would be the answer that most people would give. And the reason is because of the way we think about what simultaneous means. So what your friend will do is, because they have really perfect measuring instruments and know exactly how far away the pole and the tree are from one another, they can easily determine that the time, excuse me, at which the lightning hit the tree under which they are sitting and the time at which the lightning hit the pole are the same times, because they can go back in time, or they can estimate how far back in time that pole got hit by lightning by just using d divided by c, where d is the speed, d is the distance, 3 kilometers, and c is the speed of light. And if D over C gives them a delta T that exactly subtracts off what they measure for when that lightning bolt from the pole arrives relative to when the lightning bolt under the tree hit, then they will know that they happened at the same time. And they are simultaneous. So I should just say simultaneous, because simultaneity means that in a particular reference frame, they happened at the same time. It doesn't mean that you measure them to arrive at the same time at some, at some point. The person standing in between did measure them to come at the same time. But that was because that person was standing exactly in the middle. If you're off to the side, say underneath a tree, you can still determine that those two lightning bolts hit simultaneously if you take into account the travel time for the light from the pole to the tree. And because the two people involved in this measurement had zero relative velocity, they will both say that these events occurred simultaneously. What we'll do next time is explore what happens when that's not the case. When two things that happen simultaneously are not seen as happening simultaneously by two different observers. Okay, so we'll do that next time, and see you then. Have a good weekend.
Thank you.
Thanks, Professor.
Bye-bye.